Okay, so I'm going to review for exam 2, which covers chapters 5, 6, 7, and 8. A lot of content here. So first thing I started with is I just gave kind of a bulleted overview of each of those chapters. So chapter 5, we did double displacement, single displacement, and acid-base reactions. We looked a lot at molarity and how that works as a conversion factor for solutions. Electrolytes, remember that's really just a fancy word for ions, right, that can conduct an electric current in solutions, so dissolved ions in water. Being able to find the molarity of an unknown acid or base given titration data. Oxidation states, that's something new. So if I had, we'll look at it. I've got a review coming, but oxidation states, it's kind of like identifying the charge, but technically it's not the same as a charge, right? If I have chloride by itself -1, that's the charge. Oxidation state, they're not like true charges. So like when we look at chlorine in perchlorate, it has an oxidation state of +7. It's not like a true charge like we got from the periodic table. Figuring out what's reduced or oxidized, and with that, what's the reducing agent and what's the oxidizing agent. I've got an example coming for that. Then when we got into chapter 6, we got into gas laws. And most of this is a review from Intro Chem. So we've got our two formulas, PIVNERT and P1V1 over T1. Remember that when you use PIVNERT, right, the R constant, 0.08206, the units are picky, so liter atmosphere per mole Kelvin. And then with the P1V1 over T1, the only unit that is picky is temperature. Remember, temperature always has to be in Kelvin, and I'm sure you all remember, make sure you add that 273 or 273.15 to your Celsius temperature to get it into Kelvin. Molar mass and density of a gas, right? And what we learned in Chem 1 is how to do that when we're not at STP conditions. There are specific formulas, but I think I've mentioned this, I don't really love memorizing a bunch of different formulas. So for me, both of these are centered around a mole, so we're going to go through PIVNERT, and so I've got examples to help us review that. Collected over water, right? When that happens, we know that the pressure that's given is a mixture. It's got water trapped inside because that gas has been bubbled up through water. So we subtract the vapor pressure of water, and that'll give us our actual P1 of just the gas. A lot of times they'll refer to that as the dry gas, meaning, mathematically we removed the water. Vapor pressures of water, those are constants. You don't memorize those. The vapor pressure chart will be given. So you just have to go up to the chart and figure out what your vapor pressure is based on the temperature you're at. All right. Gas stoichiometry, if we're doing stoichiometry, we know we go through the mole. So PIVNERT is our formula of choice there whenever we're doing gas stoichiometry problems. And then KMT, kinetic molecular theory, just read that over, understand conceptually. There might be like a multiple choice question about it. And then Graham's law of diffusion, and then effusion, basically heavier gases move slower. So we just look at molar mass. So if we were comparing, for example, just H2 and O2, right? Hydrogen has a molar mass of 2.02. Oxygen is 16 times 2, so 32. So hydrogen is much faster than oxygen, right? So the heavier the gas is, the slower it'll go. When we got into chapter 7, this was finally some new material. Thermo, which is one of my favorite chapters for some reason, but we look at endothermic and exothermic reactions. We use those thermochemical equations with a delta H provided to do some stoichiometry. How much energy can we get from this reaction of 100 grams of propane or whatever it is? Be able to use Hess's law. I know sometimes students have a harder time with Hess's law, so maybe some practice there. I've got an example to help us review that. And then the other kind of fun problems I like here, and it's not just me, it's in the chapter, but it's when you have the MCAT, right? The mass times the heat capacity times the change in temperature for a substance. And what we do with a lot of these, and we'll do this in lab, is we'll take a hot metal, put it into room temperature water. The metal obviously cools down, the water heats up, and at some point that temperature equilibrates. And then we can figure out that heat exchange or whatever we want to find out, the capacity, heat capacity of the metal, whatever it may be. But that's the formula that we pass through when we're looking at substance-specific heat capacity. Not the calorimeter, but the substance-specific. All right, so then in chapter 8, This was also kind of some new material. It was looking at quantum theory. So we looked at quantum numbers. So make sure you understand the rules of quantum numbers. Your n being the principal quantum number. Your L, which is like your subshell S, P, D, or F, has a max of n minus 1. M sub L is anything from negative L to positive L. So just make sure you remember the rules for all your 4 quantum numbers. Frequency and wavelength. So the constant for the speed of light will be provided, but I do want you to remember that the speed of light is equal to wavelength times frequency. So I do want you to remember the formula, but the heat capacity, not heat capacity, I'm sorry, the speed of light constant, that 3 times 10 to the 8 meters per second, the constant will be provided, the speed of light. I just want you to remember the formula, that it's lambda times nu, or wavelength times frequency. Energy, I also want you to remember the formula. It's nice and easy. E equals h nu. But again, Planck's constant h will be provided. So all the constants are given. But I do want you to kind of understand this relationship, that the higher the frequency, the higher the energy of the photon. And then we've got our change in energy levels. And that formula also will be provided. You'll notice if you're looking at this on the very last page of the review, I repeated here what you're going to be given. So you've got your speed of light, your Planck's constant, your delta E conversion. And what I had mentioned here, I looked at it on the test. What I gave is the positive RH, and then you just swap. You could do the initial and then the final. You do, sorry, I'm writing and talking at the same time. So because we changed the order of this inside the parentheses, we changed the sign of the RH. And I don't know why I wrote RB, sorry, RH. So there's your constant. That'll be provided. All the constants will be there. I just didn't want anyone to get thrown by that. If you're used to taking the inverse of the final n squared minus the inverse of the initial n squared, when you flip it, the sign on the R, the E formula obviously also flips. So either, right, this formula and this formula is the same, but I'm pretty sure I gave it this way on the test with the positive RH. My reasoning for that is I think sometimes when I give the negative is that sometimes students miss the negative, they overlook it, and I found more issues with the positive and the negative sign being backwards. So when I did it this way, I felt like students there was no negative to miss, so that seemed to make it better. But anyway, so that'll all be provided. So first question on the review, all right, we've got sodium solid going into a solution of aluminum nitrate. Hopefully that looks to you like a nice single displacement reaction. So if we need our activity series of metals, of course we don't memorize that, that'll be given. But honestly, I think what I did on the test is I said, putting sodium solid into a solution of aluminum nitrate causes a chemical change, right? So then you know that the metals do switch places. That's always what we're looking for in single displacement. So the sodium is going to go with the nitrate. So I have to think about my charges. Sodium, group 1 metal, nitrate, -1 polyatomic. And that ionic compound will be dissolved in water. And then the aluminum now becomes the neutral solid. So what starts out neutral, right, 0 charge, becomes the cation. And what starts out as the cation, in this case +3, becomes the neutral. So that's always what we're looking at in single displacement. With balancing, because I had 3 nitrate groups to balance the charge on the aluminum, I need to make sure I had 3 nitrate groups on the product side as well. The 3 in front of sodium nitrate gives me 3 sodium, so I fixed that by putting a 3 in front of sodium on the reactant side. Now, which element here is reduced? So in single displacement, the substances that are doing the work are the metals. So never pay any attention to the polyatomic ion or the anion. We're only going to look at the sodium and the aluminum. So which one is reduced? Remember, the easy way to remember it is, this is the one that reduces its charge, right? Technically, it's because it is taking in electrons, but it's taking in negative particles, so the charge is reduced. So whatever is reduced reduces the charge. That made it easy to remember. So what I can see from here is the aluminum starts out at a +3 and goes on the product side to a 0. Right, so aluminum is reduced. All right, what is oxidized? Oxidized is when the charge goes up because we're losing electrons. What we can see is that sodium starts out as the neutral and it becomes the cation. So sodium is oxidized. Now the reducing agent and the oxidizing agent, right? Technically back here, I would say that the aluminum plus 3 is the one that's reduced. But anyway, the reducing agent is the one that's oxidized. So the thought process is whatever's oxidized, right, charge goes up because it's releasing electrons, and thus is the agent that allows for the other substance to be reduced. So whatever the reducing agent is the substance that is oxidized. So the reducing agent here is the sodium because it is supplying the electrons that allows for the aluminum to be reduced. That's the logic with reducing agent or oxidizing agent. All right, so that's a little bit of redox back from chapter 5, single displacement reaction. Then for number 2 on the review, we want to know the volume of sodium phosphate required to precipitate all the silver ions in 50.00 milliliters of 0.201 molar silver nitrate. We got to do the balanced equation first. This is a double displacement reaction. Sodium phosphate, Na3PO4. It's a solution because it has a molarity, right? So we know that that's molarities for solutions. And we're combining this with silver nitrate. All right, so on the product side, like we saw with the above question, sodium is +1, nitrate's -1, so that's balanced, +1, -1. And then the silver, which is +1, when it partners with the phosphate, which is -3, right? I'll need 3 silvers to make that work. The silver phosphates the precipitate. You will have the solubility rules given to you on the test. Phosphates are mostly insoluble, so we know that that's going to form the solid. And then just to balance, 3 silvers needed to balance the phosphate. On the reactant side, I only have 1, so I put a 3 in front of silver nitrate. That, of course, gives me 3 nitrates as well, 3 sodiums. So a 3 in front of sodium nitrate on the product side will finish that out. Now, total and net ionic. With the total ionic equation, right, every aqueous substance is going to get broken up into ions. Now, any charge balance subscript moves to the front. So instead of Na3, I'm going to write 3Na. All right, and I'm going to show that separate from the phosphate -3. Second compound, I've got the 3 silvers and the 3 nitrate groups. And then on the product side, that sodium nitrate also is going to be dissolved because it's aqueous, so those ions have dissociated. And then that silver phosphate precipitate is going to be left alone as the solid. And all of your ions should have charges, and they should all be labeled as aqueous. All right, so we've got our total ionic equation, the 3 sodiums, the phosphate, that 4 obviously stays put because that's part of phosphate, so we don't move that to the front. Then the 3 in front applies to both silver and nitrate, so 3 silvers, 3 nitrates. Product side, same, 3 silvers, 3 nitrates, and then that Ag3PO4. So sometimes the way that this will be asked is what is the sum of the coefficients, right? So if you have the right chemical equation, your sum of coefficients should be the same as mine. So we would have 3. Don't forget the 1 in front of the phosphate. So we'd have 3 plus 1 plus 3 for the silver, 3 for the nitrate. On the product side, 3 for the sodium, 3 for the nitrate. And then again, don't forget the 1 in front of the silver phosphate. So 3, 4, 7, 10, 13, 16, 17 total. So all of those coefficients. So 3, 4, 7, 10, 13, 16, 17 total. Then for the net ionic equation, we just show what makes the solid. We remove the spectators, right? Sodium isn't used here, nitrate isn't used. So what we would have left is the PO4, finding the 3 silver ions, and those coming together to make the Ag3PO4 solid. And here, if we were looking for the sum of the coefficients, 1 plus 3 is 4, plus another 1 would be 5. All right, now for the actual question. So we want to know what volume of the sodium phosphate, right, would be needed to precipitate all 50 mils of 0.201 molar silver nitrate. And we want to precipitate out all the silver ions. So basically, all that's really asking is we're just moving that reaction 100% forward, right? So we don't really have to worry about the silver specifically, we just want to make sure and precipitate all of it, right? So we start with what we've got. We have 50.00 milliliters of silver nitrate. My molarity conversion says there's 0.201 moles of silver nitrate in a liter, or 1,000 milliliters. I'm going to use 1,000 milliliters so that way that cancels out. Always in the middle, we need the mole-to-mole ratio, so 3 moles of silver nitrate on the bottom and 1 mole of sodium phosphate on top. And then because the sodium phosphate is a solution, again, molarity is what we're going to use, and that's the 0.25. So 0.250 moles of sodium phosphate on top. If you want to do a liter, that's fine, or you can do 1,000 milliliters. That's up to you. If I don't specify, you tell me. You pick which one you like. All right, so on my calculator, I'm going to take the 50.00 times 0.201, divide that by 3, and then divide that by 0.250, and then that way the factors of 1,000 cancel out. So I get 13.4 milliliters of that sodium phosphate solution. All right, so that would be the volume I would need of that solution to drive the reaction all the way forward and make sure that we've consumed all of that silver nitrate. All right. Next question, number 3, says we've got 25 mils of sulfuric acid, which is H2SO4. It's a solution, so again, aqueous. And we are going to react that with sodium hydroxide to endpoint. All right, so acid-base reaction. Since there are 2 hydrogens in the acid, we want to make sure we've got 2 hydroxides from the base. We're going to make 2 waters. And then what we have left is sodium sulfate, Na2SO4. And we've got 25 mils of the sulfuric acid combining with 35.78 milliliters of 0.5012 molar sodium hydroxide. And we want to know the molarity of the H2SO4. So this is titration data. And what I always kind of think of is if I'm solving for molarity, I need moles divided by liters. So for me, I always think of that as like a 2-step problem. I'm going to get moles of sulfuric acid first, and the way I'm going to do that is by starting with my sodium hydroxide. So for my sodium hydroxide, I start with my volume, 35.78 milliliters of NaOH, molarity 0.5012 moles per liter, or 1,000 milliliters. Now my mole-to-mole ratio, NaOH on the bottom with a coefficient of 2, H2SO4 on top with a coefficient of 1. So when I do this first part, 35.78 times 0.5012 divided by 2, and then divided by 1,000, I have 0.008, and I'm going to do 4 sig figs, 966 moles H2SO4. Then if I want to know molarity, molarity is moles per liter. So I'm going to take that number of moles, 0.008966. All right, that was our moles of H2SO4 that reacted with that many moles of NaOH in that volume and that molarity. And then I divide it by the volume that came from, which was 25 milliliters, but make sure it's in liters, so divide it by 1,000 first. And that'll be my moles per liter. So divide my moles by 0.02500, and keeping 4 sig figs, 0.3587 would be my molarity of the H2SO4. All right, so from those questions, right, that was all chapter 5 content. We looked at acid-base reactions, double displacement, single displacement. We did a little bit of redox with this first question, oxidizing agent, reducing agent. Then we did molarity and stoichiometry, and we looked at titration data. So nice little review, I think, from chapter 5. If we go to the next page, we're going to start looking at chapter 6, which is gas laws. So first question says we want to know the density of oxygen gas at 285 Kelvin and 1.06 atmospheres. Make sure that you remember your diatomics, right? And the 7 are Hofbrinkel. So when you're looking at oxygen, it's not just O, but O2, right? So nitrogen gas, N2, fluorine gas, F2. Now we want density. We know our formula, density is mass over volume, and we don't have a mass or a volume, right? So the idea with this is we're gonna assume that we have 1 mole. So the mass becomes the molar mass, which would be 32.00 grams for the 2 oxygens. The volume I'm going to get through Pivner, so that would be nRT over P. So volume, I'm assuming I have 1 mole, R 0.08206, temperature in Kelvin 285, and pressure has to be in atmospheres 1.06. So that would be my volume of that 1 mole of oxygen gas under that condition of 285 Kelvin and 1.06 atmospheres. So I get 22.1 liters. That would be my volume. Now I'm ready. Density is mass over volume. If it's 1 mole, I know it's 32.00 grams. The volume from Pivner, 22.1 liters. So when I solve, I get a density here of 1.45 grams per liter. All right, and the units for density of gases, right, grams per liter instead of milliliter because, right, mostly empty space. All right, now the next question says, we know the density. Density of the gas is 1.70 grams per liter. We're under conditions of STP, and we want to know what the molar mass is. So because we're under STP conditions, what we're going to say here is, okay, I've got 1.70 grams per liter. Molar mass needs to be grams per mole. So what I can factor in here at STP, 22.414 liters of space is the volume of 1 mole of any gas. So liters is going to cancel out, and I'm going to get my grams per mole. So if I take 1.70 times 22.414, I get a molar mass of 38.1 grams per mole. Now the question then says, if it's a diatomic, right, so this would be X2, something we're trying to find out what X. We want to know what is the identity of the gas. So what I would do then is take that 38, divide it by 2, I get 19. When I look at my periodic table, the element that has an atomic mass of 19, that's fluorine. So I know that my gas here must be F2. All right, so next question says we've got 75.2 milliliters of carbon dioxide collected through water. That's the key phrase. We're at STP. We have a reaction of excess HCl solution with sodium carbonate, and we want to know the mass of sodium carbonate that must have been present for the reaction. So we're taking HCl solution, so AQ, reacting it with sodium carbonate solid. Carbonate is a -2 polyatomic ion, so there's 2 sodiums there to balance the charge. And when I do this reaction, this was one in the chapter for double displacement reactions in chapter 5, where it talks about this is a gas producing reaction. Anytime you have carbonate with acid, the carbonate spits out CO2. And then what we would also have here is water would be made and the sodium chloride. So basically what happens is it's a double displacement where the sodium and chloride go together. That makes sense. That's like your A with D, right? Or C with B, I guess in this case, never mind. And then the hydrogen with the carbonate, hydrogen's +1, carbonate's -2, so it's really H2CO3. But I put that in quotation marks because it's not a stable compound. The CO2 comes out as the gas, it bubbles out. So 1 oxygen left to go with those 2 hydrogens, that would be your water, and then the sodium chloride would be dissolved in solution. Now, just real quick to balance, 2 sodiums, so 2 sodiums here, and then on the reactant side, because I've got 2 chlorines, I need a 2 in front of HCl. Those 2 hydrogens, those are the 2 that are in the water. So we have 75.2 milliliters of CO2 produced. And it says that we're at STP, so that means our pressure is 1 atm, or because I'm going to use the vapor pressure of water, it would be 760 torr. and our temperature would be 273 or 273.15 Kelvin. Now, because this gas, the carbon dioxide, was collected through water, that 760 atmospheric pressure would be the pressure of both the CO2 and the trapped water inside. So I need to subtract out the water, that vapor pressure of water I would get from the chart at 273 Kelvin. I know it's 4 torr. So I really have 756 torr pressure for just the CO2. What I'm looking to figure out here is the mass of the sodium carbonate that would have been present to produce that volume of CO2. So since we're going to be doing stoichiometry, we know we have to go through PIV-NERT. So the first thing we're going to do is find our moles of CO2. And moles coming from PV equals nRT. Solving for N, we would take both sides and divide by RT, so PV divided by RT. Now remember, when you're in PIV-NERT, the units matter. So the pressure of 756, I would have to divide by 760 to get it into ATM. Volume has to be in liters, so I'm going to divide that 75.2 divided by 1,000, so 0.0752 liters. R, 0.08, 206, and temperature in Kelvin, again, 273 or 273.15. So when I take the 756 divided by 760, I get 0.995 ATM. So that's my pressure in ATM. Multiply that by 0.0752 liters, divide by 0.08, 206, divide by 273.15, and I get 0.00334 moles of CO2. Now, I've got my moles of A, I got to go to moles of B. In this case, it's a 1-to-1 ratio, right? Mole to mole ratio is 1-to-1. So that means 0.00334 moles of CO2. For every 1 mole of CO2, I had 1 mole of sodium carbonate. All right, and then to get to grams, for each mole of sodium carbonate, molar mass 22.99 for sodium taken twice. Carbon is 12.01. 3 oxygens would be 48. I get a total of 105.99 for the molar mass of the sodium carbonate. So when I take that and multiply that by the 0.00334 moles, I get a mass of 0.354 grams of sodium carbonate. So that would be the mass of sodium carbonate that must have been present. Again, this was excess HCl, so we didn't have to worry about it. And that would have been the mass of sodium carbonate that would have had to have been there to generate that volume of CO2 under those conditions. All right, so a lot going on there. Remember, if you're going to do stoichiometry with gases, you're going to be going through PIV-NERT, because of course that has moles in it. And make sure with PIV-NERT, your pressure's in ATM, volume is in liters, temperature always has to be in Kelvin. And because the gas was collected through water, whenever you see that, make sure you take the pressure that's given, subtract the vapor pressure of water, and again, you'll be given the vapor pressure of water chart to go find that value. All right, so in terms of chapter 6, we looked at density and molar masses. We talked about, heavier gases move slower. We did some stoichiometry. We looked at collected through water. The only thing I didn't review, because I don't probably think it's too necessary, everybody remembers, is the combined gas law formula. So P1V1 over T1 equals P2V2 over T2. So that's the only thing that's on the list that I didn't bring on the review, but it is part of chapter 6. So just be prepared with that formula, as well as PV equals nRT. All right, now for the thermo chapter. So we've got a thermochemical equation. First thing is we're combining hydrogen with oxygen to make water in the gas phase. This is a negative delta H, so you all saw this in your chapter 7 quiz. That makes this an exothermic reaction. Energy is being released, and because there's so much energy being released, the water that's coming out is hot. It's in the gas phase, right? It's not liquid. And we want to know how much heat is released. So you can almost sort of think of this as your B. When you produce 675 grams of water by combining those two gases together. All right, so we're going to have our 675 grams of water as our starting point. We know to always go to moles first. 1 mole of water, 18.02 grams is the molar mass from the periodic table. And we get negative 484 kilojoules released every time we produce 2 moles of H2O. Sorry, that's supposed to be an L. All right, so my energy, 675 divided by 18.02, meant I had 37.5 moles of water produced. For every 2 moles of water, I get 484 kilojoules released. So to 3 significant figures, I get a total of 9,060 rounding. I had 9,064.9, so I'm going to round that to 9,060. 3 sig figs. All right, so that is your heat, and it is released. All right, so that is a nice example of a thermochemical equation, and using that delta H as a conversion factor. Remember, you can relate delta H to any substance in the equation. Just make sure you use that coefficient that's in the balanced equation. We get negative 484 kilojoules every time we produce 2 moles of water. So that's what we want to make sure and capture, 2 moles of water. All right, so next page, another thermochemical equation, or at least we're trying to get there. It says 228 kilojoules of heat is released. So again, we're going to know here that delta H is less than 0, going to be negative, another exothermic reaction, when 64 grams of oxygen is combined with excess NO. And we want to know the delta H for the reaction. All right, we already talked about it is exothermic because it's got a negative delta H. Energy is being released. So what we're looking at here is making our own kind of delta H value. So if delta H, we get negative 228 kilojoules, right? Every time, or in this example where we use 64.0 grams of O2. So what we have is our heat per mass, and what we want to do is just change it into per mole. All right, and we would do molar mass for that. So getting rid of grams, right, and then moles would be on the bottom because your delta H values, it would be per 1 mole of O2. Sometimes students like to do this kind of step by step first, and they take the 64 grams, divide it by the 32 molar mass. You can see you have exactly 2 moles of oxygen, and then take that 228 and divide it by 2. That's another way to do it. All right, so what I get here is a negative 114 kilojoules. Technically per mole, but that's implied when you have your delta H for the reaction. And again, exothermic energy is being released. All right, now the other part in thermochem, right, we looked at endothermic and exothermic. We solved for the enthalpy of a reaction. The specific heat calculation, I didn't put that on the review, so make sure you look at those calculations in the Chapter 7 practice quiz or credit quiz. But this Hess's law, for some reason, like I said, and it's unfortunately, it's one of those where it's kind of all or nothing in the points, the way that it's set up. So what you want to do is you look at the thermochemical equations that are given, and you look for substances in the target. I call that the target equation, the one that we're trying to find delta H for. And you look for substances that are discrete, right? They only come from that reaction. So like chlorine, what I notice is I've got it in 2 different reactions here. So that's going to be a tough one to look at. Methane, however, the CH4, only comes from this first reaction. So I'm going to manipulate this first reaction, and I always want to ask myself 2 questions. So when I take this first reaction, the first thing I'm going to say is, does it have the correct coefficient in front? Yes, 1 and 1. So that's good. The only other thing I can do then is ask myself, does it need to be flipped? And the answer is yes. Methane is on the reactant side, here it's on the product side. So we're going to flip that equation. So we're going to have CH4 turning into the carbon and the hydrogen, the 2 H2s. When you flip the reaction, you change the sign of the delta H. So it was exothermic, right, but now it's going to be endothermic. Now, the next substance, so we took care of the methane. We had talked about chlorine, we're not going to worry about. Let's go to this carbon tetrachloride. Carbon tetrachloride only comes from this second equation. I don't see it anywhere else. So again, same two questions. Is it on the correct side? Yes. Product side, product side. Does it have the correct coefficient in front? Yes, 1 and 1. So for equation 2, I'm just going to leave it as is. So I'm going to take carbon, 2 chlorines, and turn it into carbon tetrachloride. Delta H stays the same, negative 95.7 kilojoules. All right. Last substance here is the HCl. That is only coming from this third equation. So now for my third equation, same two questions. Is the HCl on the correct side? Yes, product and product. Does it have the right coefficient in front? No. It has a 2, I need it to have a 4. So I'm going to multiply that equation, the thermochemical equation, by 2. So I'm going to have 2 hydrogens with 2 chlorines making 4 HCl. And when you multiply the equation by 2, it makes sense. You're going to get twice the energy released, right? So we're going to take that negative 92.3 and multiply that by 2. So what I get here for my new delta H value is negative 184.6. All right. Now I'm going to add all of my equations together, right? And like terms on opposite sides will cancel out. So I've got 2 hydrogens on the reactant side, 2 hydrogens on the product side, canceling out. A carbon on the reactant and a carbon on the product will cancel out. And what I'm left with is the thermochemical equation that I was looking for. I've got the methane reacting with 2 plus 2, so 4 chlorines, to make the carbon tetrachloride and the 4 HCl. So what I'm going to do is I'm going to add all of those delta H values together. So I'm going to take the 74.4, I'm going to add it to a negative 95.7, and I'm going to add it to a negative 184.6. So I get a delta H of a negative 205.9 kilojoules. Since you're adding there, you want to keep the decimal place, right? So everything goes to the tenths place there. All right. So that's Hess's law. Now for the remaining material, chapter 8, quantum numbers, energies of transitions, right? So this question number 10 is going to kind of put almost everything, just not quantum numbers, into one question. And again, just to make sure, right, all this information here is going to be provided. Okay. So we're taking an electron, relaxing it from an outer shell of 6 to an inner, more closer to the nucleus shell of 2. So right there, I want you to think, okay, it's relaxing. This is going to be an exo process. So we know right there that the energy of that transition should be negative, right? So first, let's find that energy. So delta E would be equal to the RH, the 2.179 times 10 to the negative 18 joules. And again, I'm using the positive start. So we're going to take 1 over the initial squared. The initial is a 6, so this would be 36, because 6 squared, minus 1 over the final squared. 2 squared would be 4. All right, so on my calculator, I'm going to take the inverse of 36, which is 0.027777, minus the inverse of 4, which is 0.25. So I get my 2.179 times 10 to the negative 18 joules times negative 0.22222 repeating. So when I multiply by 2.179 times 10 to the negative 18, all right, the change in energy for that transition is negative 4.84. 2 times 10 to the negative 19 joules. All right, so that would be exothermic. So you always kind of know that going in. If the electron is getting closer to the nucleus, that makes it happy. Energy is going to be released. That's stabilizing, right? So you always can kind of go in, like if you forget your negative sign or you swapped your final initial by mistake, you can always just double check that. If you're getting closer to the nucleus, your delta E of transition should be negative. If you're going away from the nucleus, right, you're going to have to put energy into that, so delta E would be positive. All right, so we got the energy. Now we want to look at the frequency. And so the relationship between energy and frequency is E equals h nu. And again, on your sheet, Planck's constant, right, will be given to you. So don't worry about memorizing that. Now, here's what's a little strange. The frequency, right, cycles per second can't be negative. So we're going to take the absolute value of that energy. So our energy is 4.842 times 10 to the negative 19 joules. All right, and we're going to divide that by Planck's constant, 6.63 times 10 to the negative 34 joules seconds. And that'll get me my frequency, or my nu, right? So I've got my answer still in the calculator from before. Divide that by 6.63 times 10 to the negative 34. And I get 7.30 times 10 to the 14. You can either do per second, because that's what units you have, or you could use hertz. So 7.30 times 10 to the 14 hertz, that would be my frequency. All right, so cycles per second. Now if we want to know the wavelength, that's where we need the speed of light. So if I know that c is equal to lambda times nu, what I'm going to do is solve for lambda. So I'm going to divide both sides by nu. So when I take my speed of light, the 3 times 10 to the 8 meters per second, divide it by my frequency, 7.30 times 10 to the 14 per second, I'll get my wavelength. All right, so I get here 4.11 times 10 to the negative 7 meters. All right, or if I multiply that by 10 to the 9, that would be 411 nanometers. All right, so that would be in the visible spectrum. And what we had talked about was anytime you end with an n of 2, that's the Balmer series. So when your final energy shell of a transition is the second shell, it always turns out to be in the visible spectrum. All right, which is just kind of fun to know. All right, then the last thing for the review are the quantum numbers. So we want to look at the quantum numbers for the valence electron in cesium. All right, so cesium is Cs. Valence electron is the outermost electron. So when I look at cesium on my periodic table, it is in row 6, and it's in the S block, and it's the first spot. So because we're in the 6th row, we know our n is equal to 6, right? Principal quantum number, nice and easy. Because we're in an S subshell, we know that our L value is 0, right? Because we know when it's S, L is equal to 0. If it's P, that means L is equal to 1. If it's D, L is equal to 2. That's supposed to be an L, sorry. And then if it's an F, your L value is equal to 3. Your M sub L values can be anything from negative L up to 0 up to positive L, increasing by whole numbers. So in this case, because my L is equal to 0, in this particular example, M sub L can also only be equal to 0. And then M sub S, positive 1/2. The positive or negative 1/2 to me, like, how are you going to prove that? Like, which way is the electron spinning? So to me, that's either a plus or minus always with the answer with the spin quantum number. So plus or minus 1/2, both are fine. I don't think anybody could argue that the electron is spinning one way or the other. So quantum numbers, when you find your n value, right, whatever that is, your max value for L is n minus 1. So technically if n is 6, we could even go up to an L of 5. But remember, those are all theoretical values. On the periodic table, we don't have anything past an L value of 3. M sub L is anything from negative L to positive L. So if I had a D subshell, my M sub L would be negative 2, negative 1, 0, 1, and 2. In this case, though, because L was 0, M sub L can only be 0. And your spin quantum number is just plus or minus 1/2. That reminds us of electron configurations and orbital diagrams, that within an orbital, those two electrons will have opposite spins. So that's why M sub S is either plus or negative 1/2. All right, so hopefully that was a nice review for test 2.